Hi and welcome back. Very recently, the one-way ANOVA test got added to the curriculum here at our community college. So this will be the last hypothesis test that we run together. I know some colleges stop before that, some colleges stop after that, but the one-way ANOVA will be the last one for us. Okay, analysis of variance. ANOVA. It's an inferential method used to test the equality of three or more population means. And here's just a sort of note of caution right here. I'm going to circle that. So if you're, do not test the null that mu1 equals mu2 equals mu3 by conducting three separate hypothesis tests, because the probability of making a type 1 error will be much higher than alpha. So in other words, when some people are comparing, let's say, three means, they're sometimes inclined to do combinations of each, mu1 against mu2, mu2 against mu3, mu1 against mu3. They're inclined to compare one by one. You don't want to do that. You can actually run a one-way ANOVA, which is what we're about to do. So let me keep reading here for you. Requirements, and I'll insert this here. Requirements to run the one-way ANOVA is that there must be k simple random samples, one from each of k populations or randomized experiment with k treatments. The k samples are independent of each other, that is, the subjects in one group cannot be related in any way to the subjects in a second group. So, for example, if you're working on twins or mothers and daughters or somebody that's genetically linked with respect to the parameter of interest, that would be a match pairs test. That wouldn't be this. The populations are normally distributed, and this is a funny one, this last one. The populations must have the same variance, or arbitrarily close, and they're going to be perfectly the same, but that is, each treatment group as coming from a population with variance sigma squared. Now, in order to really test that, you would have to run, I was going to write here, an F-test, so to test that the variances are the same. We don't learn that this term, but your author is letting us use this lovely rule of thumb right here. And I'm going to page down to that. And so it says here, as a rule of thumb to test for equality of variances, the one-way ANOVA procedures may be used if the largest sample standard deviation is no more than twice the smallest sample standard deviation. So for us, rather than running an F-test to check that constraint, we'll do that, rule of thumb. Okay? A little bit now on the null and research hypotheses, which is right here. Your null hypothesis regarding three means is going to be that mu1 equals mu2 equals mu3. Your H1 is going to be that at least one population mean differs from the others. A little side note I have here. The methods of one-way ANOVA are robust, so small departures from the normality requirement will not significantly affect the results of the procedure. In addition, the requirement of equal population variances does not need to be strictly adhered to, especially if the sample size for each treatment group is the same. Therefore, it's worthwhile to design an experiment in which the samples from the populations drawn are roughly equal in size. Okay, let's try an example. We have two examples that we're going to be running today, and I'd like to figure out how to do it on Megastat Excel and also in the calculator. The following data represent the weights. So, oops, let me highlight there. Here we are. So the following data represent the weight in grams of pennies minted at the Denver. Apparently I cut that off of the page. At the Denver Mint in 1990, 1995, and 2000. Verify that the requirements in order to perform a one-way ANOVA are satisfied. So we have our three data sets. We are assuming that they are simple random samples. Okay, so the three samples are simple random samples. They are obtained independently. If we were to make normality plots, normal probability plots on Minitab, we would see that the data are approximately linear, so the normality assumption is satisfied. We talked about the fact that we don't have Minitab during a test situation, so we would look at box plots to make sure there aren't any extreme outliers. The sample standard deviations are computed for each sample using Minitab, as I pasted below, and we test for that last constraint that the population variances have to be equal. Instead, we see, does the largest standard deviation, that it's not more than twice the smallest standard deviation, and that's satisfied. So let me show you the output. And remember, you could retrieve this output from Excel, Minitab, anything you wanted really, graphing calculator. So let's take a look at the standard deviations. Notice that the smallest one is the 0.014. And if you take twice the 0.014, you get, about 0.028. And 0.028 is still greater than the largest sample standard deviation that's in the list. So you really just take double the smaller, and if that's still bigger than the largest sample standard deviation on the list, the requirement of the equal population variances is considered satisfied. Okay? And that's actually easier than running an F-test, so. Okay, let's take a look at the next page. So we're getting ready to run the test. The basic idea in the one-way ANOVA is to determine if sample data could come from populations with the same mean, mu, or suggest that at least one sample comes from a population whose mean is different from the others. To make this decision, we compare the variability among the sample means to the variability within each sample. We call variability among the sample means the between sample variability. Okay? And the variability, sorry, my computer went offline there for a bit. Let me reread constraint number 2. We call the variable among the sample means the between sample variability, and the variability of each sample the within sample variability. So I know there's a lot of language there, and I don't require my students to compute this by hand. I just want them to be a little bit familiar with it. We're actually going to retrieve the F-test statistic from the software. If the between sample variability is large relative to the within sample variability, we have evidence to suggest the samples come from populations with different means. Now, actually calculating that between sample variability and within sample variability is somewhat tedious. So like I said, I won't make you do that by hand. I just want you to understand the notion of it. So it will be an F-test statistic with the one-way ANOVA. And your F-test statistic is, like we said, it's the between sample variability divided by the within sample variability. Another way of saying that is that it's the mean squared due to treatments divided by the mean squared due to error, sometimes called the MST over the MSE. So you will see when we run these tests, you'll see that F-test statistic reported. Okay, let's see the next slide. Oops. Oh, now we're actually ready to run the test. Okay, so you see I've pasted the data from the coins from the various years into Excel. So let's go to add-ins, Megastat. Now we're going to go to analysis of variance, one-factor ANOVA, one-way ANOVA. Okay. Input range, you can just highlight the data, not the years. And then the post hoc analysis, Tukey's test, we don't really talk about that much this term. I have here, show it when the p-value is less than 0.05. Hit OK. Now what you'll see here, let me scoot this over, what you'll see here is that we're going to retrieve, let me zoom this out here so you can see the F-test statistic. What we're really going to do is just retrieve the F-test statistic and the p-value. Now if you're really curious about degrees of freedom here, you have a degrees of freedom for treatment, a degrees of freedom for error, and then the total degrees of freedom, which is 32 in this case. I don't want you to get too hung up on the degrees of freedom since this is the last test we're running. I just want you to report the F-test statistic, which is 1.11, the p-value, which is 0.34, and now you know the golden rule. Since p is greater than alpha, we fail to reject H0. Kind of means accept H0, but you're not really allowed to accept it for sheer truth. You can only say I don't have enough evidence to say otherwise. So there's not enough evidence. To say that one mean significantly differs from the other. To say that at least one mean differs. One population mean significantly differs from the other. Okay, so a way of saying that is here we have a large p-value. We don't have enough evidence to support the research hypothesis. Okay, let's try taking a look at one where perhaps the p-value ends up significant. So I have another test here. This one I'd like to read it to you first. It says a medical researcher wishes to try these 3 different techniques to lower cholesterol levels of patients with high cholesterol levels. The subjects are randomly selected and assigned to one of 3 groups. Group 1 is given medication, Group 2 is given an exercise program, and Group 3 is given a diet program. At the end of 6 weeks, their cholesterol levels are recorded. Find the F-test statistic to test the hypothesis that there is no difference among the means. Now remember, your null would be that mu1 equals mu2 equals mu3. And your H1 would be that it, just like it says there, that at least one differs. At least one mean differs significantly from the others. Okay, and it tells us, use 0.05 is fairly typical. Use the 0.05 alpha level. Okay, so what I did, I don't know if you can see those numbers, they're pretty small, so I put them in Excel. Here they are. Let's zoom that a little bit. So I put the 3 groups and their respective data in Excel. Let's run the ANOVA test. So add-ins, Megastat, ANOVA, 1-factor ANOVA, input range, and you just highlight the data, not the G1, G2, and G3, but the data itself. And post hoc analysis, when p is less than 0.05, that's not required for our course, but I think it's interesting. Let's take a look. Okay. The p-value is significant. Notice we're going to report this. The thing that we're going to report is the F-test statistic, which is 11.09. We're going to report the p-value, which is 0.0011. Now we know, since p is less than alpha, we reject H0. We favor H1. Thereby we favor H1. So there is enough evidence to say that one mean significantly differs from the other. To say at least one mean, possibly more. Differs from the rest. Now what's neat is the Tukey's post hoc analysis, Tukey test. Let's just take a look at that for grins and giggles here. What's neat is the Tukey test, it will do the pairwise t-test for you. And if you zoom in here, it's p-values for the pairwise t-test. If you zoom in, it'll show you which ones differ most significantly. So G1 against G2 had a p-value of 0.0003, but they're all significant. Even G3 against G2 has a p-value of 0.0485. So, and you compare that to a 5% alpha level, they're all significantly different. G1 against G3 has a p-value of 0.02. Okay, so Tukey test will give you the p-values for the pairwise t-test, which is very nice. Okay, and even if you look at it visually, let's look at this graph here real quick. If you're a visual person and you just want to get a feel for the data, see the comparison of groups, you can see that this group differs most significantly from this group, and that's exactly what that p-value was indicating. Okay. All right, that's as far as we need to get for the one-way ANOVA. And like I said, don't worry too much about the degrees of freedom. You are noticing that there were 3 groups and 3 less 1, the treatment. So the degrees of freedom for the treatment group are the number of groups, G1, G2, G3, minus 1, so that's where that 2 is coming from. And then if you look at the actual data, you're probably wondering where the 15 degrees of freedom under error. In case you are wondering about that, you'll notice it 1, 2, 3, 4, 5, 6. 6 times 3 is 18 total observations. But if you take 18 minus the 3 groups, 18 minus 3 is 15. So that's where the degrees of freedom were coming from for that error. But like I said, this is the very last test that we run, so I'm not going to make you delve too deeply into where the degrees of freedom came from. Or even here you have the MST over the MSE. You're noticing that if I take the MST over the MSE, I'm getting that F-test statistic. Okay? All right, good luck out there, and happy studying.